Hi, my name is Julien Tierny, and I'll be presenting our work on the discrete Morse sandwich. So this work deals with the computation of the persistence diagram, which is a central representation in topological methods. It consists of bars, which encode the topological features which appear and disappear in the data as you sweep it from bottom to top. And in this example, the two green bars correspond to the two main hills, and the small blue bar corresponds to the pit, and the large blue bar indicates that there's a single connected component in the domain. So the x value of a bar corresponds to the creation time of the feature in the sweep, while the y-coordinate of its top point indicates its destruction time. And then the height of the bar is called persistence. An interesting aspect of this diagram is that it is robust to additive noise. As you can see on the right, despite the noise, we can still identify the main features from the original diagram, such as the two hills and the pit. In visualization, persistence has been used as a key criterion to guide feature selection, in eddy extraction, for instance, or filament extraction, or data segmentation. Up to now, TDK included an algorithm for persistence diagrams which was fast in 2D but slow in 3D. And in terms of literature, one of the very first algorithms is due to Adelsbruner and co-authors, and we'll call it the standard algorithm. Recent variants reformulate this approach in terms of the reduction of the boundary matrix of the data. And another line of work based on discrete Morse theory focused on computing an intermediate data representation called the Morse complex, which is usually smaller than the original data, and then they run the standard persistence algorithms on this reduced representation. And as you will see next, our work is also based on discrete Morse theory, but it does not compute the full Morse complex. And instead, it can be interpreted as a modern variant of the standard algorithm by Adelsbruner et al. So this work makes the following contributions. First, we introduce a fast algorithm for persistence diagram computation for scalar fields. It can be seen as a reinterpretation of the standard algorithm with discrete Morse theory. We combine it with a global strategy that we call the sandwiching, which computes the easiest dimensions first in order to eliminate candidate critical simplices before running the slowest part of the algorithm. We provide an open source implementation, which is now the default backend in TTK. And we provide a reproducible benchmark package, which automatically downloads data from public repositories and compares the running times and outputs of a selection of open source implementations. So now we'll recap the main steps of the standard algorithm. So this algorithm pairs every d+1 simplex, which destroys a feature, to an unpaired d simplex, which created the feature. To do so, it processes the data in reverse order to go from the destructors to the creators. And at each step, it grows the boundary of the destructor sigma I in a way that is homology preserving. And the process continues one simplex at a time until we reach an unpaired d simplex, which is then marked as the creator of the feature destroyed by sigma I. And this process is shown here for triangle sigma I. We consider its boundary, and we grow it by selecting at each time the highest edge tau of the cycle, here in yellow. And next, the cycle is extended by adding the cycle associated with tau. And in this example, tau was paired with the adjacent triangle on the left, so we just added its boundary. And we continue this process until we find an unpaired edge here in blue, and we pair it with the input triangle sigma I. So now, a key observation with this algorithm is that it creates a large number of pairs with zero persistence. For example, the insertion of Vi in the sweep creates a connected component, which is immediately merged by an insertion of the next edge. Or the hole created by E1 in the sweep is immediately filled by the next triangle here, and so on. So to skip the computation for these unnecessary pairs, we rely on discrete Morse theory. And specifically, we rely on the discrete gradient computation algorithm introduced by Robbins and co-authors. This algorithm pairs d simplices with one of their adjacent d+1 simplices, as shown with these little vectors here at the bottom. As detailed in our paper, it turns out that all the simplices involved in a vector are guaranteed to be also involved in a zero persistence pair. So we create a zero persistence pair for each vector. And we only run the standard algorithm for these simplices which are involved in no vector at all, and which are called critical simplices. And these are the largest spheres here, there. We present an extra acceleration, but I invite you to check the paper for further details. All right. At this point, we can run the standard algorithm only from the critical simplices and already get a good speed up, but we can go further by considering an overall strategy that we call sandwiching. And the key idea is to compute the simplest dimensions first. For instance, we show in the paper that for the persistence pairs involving edges and vertices, the standard algorithm, when it is applied to critical simplices, only visits edges located on discrete integral lines, linking one saddles to minima, here in blue. So we create the graph of these integral lines, and we efficiently track connected components in this graph with a union find, which quickly gives us the persistence diagram for the homology of dimension 0. By duality, we apply exactly the same process for the diagram of dimension 2, by processing integral lines connecting two saddles to maxima. And then, for the dimension 1, we only need to use the standard algorithm for the remaining critical points. And at this point, for most data sets, there isn't that many anymore, hence the significant accelerations. So to evaluate our algorithm, we designed a reproducible benchmark available at this address. And that benchmark downloads data from a public repository and compares the runtimes and outputs of a selection of implementations. So to guarantee unbiased comparisons, we focused mostly on these implementations which natively supported simplicial complexes. And we first tried to evaluate the practical correctness of our implementation. And we did this by computing the Wasserstein distance between the diagrams computed by our approach and those of competing approaches. And it turns out that for most methods, including our textbook implementation of the standard algorithm here at the top, the distance is exactly 0, which means that our implementation provides the exact same result as these methods. And for the other algorithms, this distance is larger, which seems to indicate slight inaccuracies in these implementations. So now we compare the computation speed as a function of the output size for 1D, 2D, and 3D datasets. And for all cases, when computing with 8 cores, our approach in dark blue provides the fastest computations. So since our approach explicitly grows the cycles when applying the standard algorithm, we can store them in order to later visualize the most persistent ones. And this can be useful, for instance, to extract surface generators in geometry processing, or to identify the atom rings with the most variation in electron density in quantum chemistry, or to identify the most important loops in the cosmic web. And as detailed in the paper, we can also apply this algorithm to identify circular patterns in abstract point cloud data. Alright, so in conclusion, we presented a fast algorithm for the computation of persistence diagrams of scalar fields. Our implementation provides identical outputs to reference implementations, including our textbook implementation of the standard algorithm. Our algorithm is output sensitive and faster in practice than competing methods, and it also has a good memory footprint. And this research is reproducible. Our implementation is included in TTK, and it is now the default backend for persistence diagram computation. Our paper has been certified as replicable by the Replicability Stamp Initiative. The benchmark package is available at this address. And the TTK online example database now includes the application examples I showed you regarding the extraction of persistence cycles, so it should be easy for you to experiment with this application on your data. All right, and that is it for my talk. Thanks for your attention.